Today, we're plunging into some truly mind-bending physics. We're tackling a concept that aims to bridge probably the biggest divide in modern science. The gap between the vastness of the cosmos and the sheer weirdness of the quantum world. Our source material for this deep dive is drawn from an analysis titled Spacetime Emergence from Entangled Gravitational Strings. Hey. Now, this is definitely an expert-level breakdown exploring a highly speculative, but I have to say, incredibly intuitive model for, the fundamental structure of reality itself. Our mission for you today is to unpack this proposal, So what does this all really mean? Let's get into it. Okay, so modern physics, as we know it, really stands on two colossal pillars. You've got Einstein's general theory of relativity.
Right. Describing gravity as space-time curvature, planets, galaxies, the big stuff.
Exactly. And then on the other side, there's quantum mechanics.
Which handles the probabilistic, often really counterintuitive rules of the subatomic realm.
The strange world of particles.
Yeah. And what's fascinating here, or maybe frustrating, is that these two theories, despite all their individual successes, are just fundamentally incompatible.
How so?
Well, general relativity is smooth, its deterministic things follow predictable paths. But quantum mechanics, it's discrete, jumpy, probabilistic. It deals in likelihoods.
Right. Probabilities, not certainties.
Precisely. And this clash, this incompatibility, it's arguably the greatest unsolved problem in fundamental physics. We're talking brilliant minds grappling with this for nearly 100 years.
Wow. Okay, so into this epic challenge steps this proposed model. It suggests a universe made of stringified particles. So fundamental things aren't just points, they're connected by strings formed by gravity itself.
That's the initial idea presented, yeah. And here's where it gets really interesting, as the analysis points out. These strings are supposedly manifestations of quantum entanglement.
Entanglement. Okay, like Einstein's spooky action.
Exactly that. Each string's endpoints represent a pair of entangled particles. The particles themselves are seen as point-like at the very ends, but the whole connected system behaves like a stringified wave.
A stringified wave. Okay, we'll need to unpack that.
We will, but it's important to note this isn't some, totally fringe idea pulled out of thin air. It's framed as a serious synthesis of cutting-edge, albeit speculative, concepts. It draws heavily from string theory, obviously, but also this newer idea of emergent spacetime.
Right. So to really grasp this new model, we probably need a quick refresher on the giants it's trying to unify. Let's start with the standard model of particle physics.
Okay, so the standard model, it's been incredibly successful. It describes matter as fundamental particles, fermions, like quarks and electrons.
The building blocks?
And then force carriers, bosons, like photons for electromagnetism. And these are usually treated as zero-dimensional points with specific properties.
And experiments back this up incredibly well.
They do, but it has limits.
Right.
Those famously.
No gravity.
Exactly. No gravity. And if you dig deeper, you get to quantum field theory, QFT. QFT tells us particles aren't really tiny balls. They're more like localized excitations, ripples in underlying fields that fill all of space.
So an electron is a ripple in the electron field.
Precisely. An elegant picture, but that point-like nature, even as a field excitation, it causes real mathematical problems when you try to add gravity. You get infinities.
Ah, the infamous infinities.
Right. And unlike with other forces where we can sort of mathematically sweep under the rug renormalization, it's called, with gravity, these infinities are intractable. They just won't go away. This basically means QFT and gravity don't mix at high energies. It's a huge motivation to think beyond point particles.
Which also brings us to that other quantum weirdness, wave-particle duality.
Yes. How can something be both a wave, spread out, interfering with itself, and a particle detected at a single point?
It depends on how you look at it, right?
It does. Quantum objects, like electrons, show both sides depending on the experiment. We describe this with wave function, a mathematical tool for probabilities.
But what is the wave function physically?
That's still debated. Is it real? Is it just information? This proposed model's stringified wave idea is actually a really novel attempt to give this abstract wave a physical geometric structure, something tangible.
Okay, so the problems with point particles pushed physicists towards, strings. The string revolution.
Yes, starting roughly in the late 60s. String theory basically says the fundamental things aren't points. They're one-dimensional vibrating filaments of energy. Strings.
Incredibly tiny, right? Like Planck length tiny.
Unimaginably small, yes, around 1035 meters. And the key idea, the really beautiful part, is that different ways these strings vibrate correspond to different particles. An electron is one note, A photon is another note, a quark is another.
So everything, all the particles are just different vibrations of the same basic thing.
Exactly. It's a profound unification. All matter, all forces, just different tunes played on these fundamental strings.
And these strings, they can be open or closed.
Correct. Open strings have two distinct ends, like a little piece of, well, string. Closed strings form loops. Open strings actually led to this related concept of D-branes. Think of them as higher dimensional surfaces or membranes that the ends of open strings can attach to.
Okay, membranes in spacetime.
Yeah, and this idea, it sounds abstract, but it later provided a really powerful potential explanation for why gravity seems so much weaker than the other forces.
Ah, okay. We'll come back to that. But the biggest win for string theory initially.
Gravity, hands down. It naturally incorporates a quantum theory of gravity.
Oh.
When theorists analyzed the vibrations of closed strings, loops, they found one specific vibration mode had the exact mathematical properties needed for the graviton.
The hypothetical particle carrying the gravitational force.
The very one. It wasn't something they had to add in. It was an unavoidable prediction of the theory itself. And because strings aren't points, they're expended objects, when they interact, the interaction is sort of smeared out over a tiny region.
Which avoids those infinities.
Exactly. It smooths things out and resolves those mathematical nightmares that plagued earlier quantum gravity attempts.
Okay, that sounds amazing. But there's a catch, isn't there? A big one.
Several, actually. The most famous one is dimensions. For the math to work consistently, most string theories need 10 space-time dimensions.
10. But we only see 4, 3 space, 1 time.
Right. So the idea is that the extra 6 spatial dimensions are compactified. They're curled up incredibly tightly into complex shapes called Calabi-Yau manifolds, far too small for us to see directly. The specific geometry of these hidden dimensions would, in theory, determine the fundamental constants and laws of physics we observe in our large dimensions.
That sounds complicated.
It is. And there's another ingredient. Supersymmetry, or ZUEY. It predicts every known particle has a heavier superpartner with different spin properties.
And have we found any evidence for extra dimensions or these superpartners?
No, not yet. Decades of searching at particle colliders like the LHC, and nothing definitive has turned up. That's a major challenge for string theory, no doubt about it. Hashtag, tag, spooky connections, and emergent spacetime.
Okay, so alongside string theory, there's this other radical approach emerging, particularly from quantum information science. The idea that spacetime itself isn't fundamental.
Exactly. That spacetime emerges from something deeper, specifically from quantum entanglement.
Ah, back to the spooky action at a distance.
Mm-hmm. Entanglement is this bizarre quantum link between two or more particles. Their fates are intertwined no matter how far apart they are. Measure one.
And you instantly know the state of the other.
Instantly. Experiments confirm it's real, it's fundamental. It's a key resource for quantum computing and communication, too. Though, crucially, it doesn't let you send information faster than light.
Okay, but how does this connect to space-time geometry? You mentioned ER, EPR.
So, connecting this to the bigger picture. In 2013, Juan Maldacena and Leonard Susskind put forward this really provocative conjecture, ER-EPR. It proposes that a pair of maximally entangled particles, that's the EPR, named after Einstein, Podolsky, and Rosen, who first highlighted the paradox,
Okay.
is actually equivalent to an Einstein-Rosen bridge. That's the ER, which is basically a wormhole.
Wait, entanglement equals a wormhole, a geometric connection through space-time.
That's the proposal. The non-local quantum connection of entanglement has a geometric dual, a physical connection, a shortcut through space-time.
Whoa, so space-time isn't just the stage, it's actually made of these entanglement links.
Precisely, that's the emergent space-time idea. Space-time is built, constructed from the pattern of entanglement between quantum systems. Entanglement is the glue holding space together. If you decrease entanglement between two regions,
They effectively move farther apart in the emergent geometry.
that's the duality. This it-from-qubit idea reality woven from quantum information is a really powerful modern lens, and it's crucial for understanding the proposed model we're discussing.
Okay, let's dive back into the specific model from our source analysis, starting with its first core idea about how these strings originate.
Right. The analysis quotes the model as saying, particles are stringified by gravitational forces. Now, taken literally, this implies a cause and effect. You have particles, gravity acts on them, and then you get strings.
Particles plus gravity yield strings.
Yeah. But as the analysis points out, this phrasing directly contradicts standard string theory.
Where the strings are fundamental and particles and gravity come from the strings vibrating.
Exactly. Standard string theory reverses that causality. Strings come first.
But the analysis mentions an analogy that makes this gravity makes strings idea feel kind of intuitive, doesn't it, from particle physics?
Absolutely. A really strong analogy comes from quantum chromodynamics, QCD, the theory of the strong nuclear force that binds quarks together inside protons and neutrons. If you try to pull two quarks apart, the strong force between them doesn't spread out like electromagnetism. Instead, it forms a narrow flex tube, essentially a string-like object carrying energy.
A literal string made of the strong force field.
Pretty much, it has constant tension, meaning it takes more and more energy the farther you pull them, until eventually it's energetically cheaper to create a new quark-antiquark pair from the vacuum, breaking the string. This QCD flex tube strings the quarks together.
Okay, I see the parallel. So the idea is maybe gravity does something similar, creates gravitational flux tubes.
That's the intuition the model seems to tap into, and it's actually an idea explored in some, more speculative modified gravity theories. It feels physically plausible in a way.
Okay, but how does the model square this with the ER-EPR idea we just discussed? How does entanglement fit in?
Ah, this is where the second key statement from the model becomes absolutely crucial according to the analysis. Each end of the strings is an entangled particle.
Okay.
When you view the model through that lens using ER-EPR, the whole picture shifts. It becomes remarkably insightful. The gravitational string isn't something created by gravity acting on pre-existing particles. Instead, the gravitational string is the Einstein-Rosen bridge, the wormhole, that ER-EPR says is equivalent to the entanglement between the particles at the ends.
Ah, so stringification by gravitational forces isn't gravity actively making a string?
No, it's more like the gravitational description. The wormhole geometry is the emergent manifestation of the underlying quantum entanglement.
The wormhole is the entanglement seen from a geometric perspective.
Exactly. It's the emergence of geometry from quantum information. The gravity description is the large-scale classical view of this quantum connection. This reinterpretation, using ER-EPR, suddenly aligns the model perfectly with this cutting-edge emergent spacetime research. It makes much more sense.
So, if ER-EPR is right, does that mean literally any pair of entangled particles anywhere in the universe is connected by a tiny wormhole?
That's the mind-bending implication, yes. The conjecture suggests that indeed, any entangled pair has a corresponding Planck-scale wormhole connecting them.
What does that imply for spacetime itself? Is it riddled with these tiny wormholes?
It would mean spacetime isn't the smooth, continuous background we usually imagine. Instead, it would be this incredibly complex, dynamic network of quantum connections, a vast web of entangled particles linked by these microscopic wormholes. The geometry we perceive, distances, curvature, would emerge from the pattern and density of these connections. That fits perfectly with the model's core intuition, interpreted this way.
Okay, and the final piece. The model says particles are point-like at each end, yet they behave as stringified waves. How does that work?
Well, the point-like at each end part aligns okay with how QFT treats particles locally. But the crucial insight is that these points aren't independent. They are fundamentally connected by the string, the wormhole. And this string wormhole has a minimum length, roughly the Planck length. So there's a fundamental minimum separation built in.
Ah, so interactions can't happen at an exact single point.
Right. It effectively smears out the interaction, preventing it from becoming infinitely strong at zero distance. This is conceptually very similar to how standard string theory tames infinities by replacing points with extended objects.
And the stringified wave part, what's the insight there?
This, I think, is where the model, seen through ER-EPR, is perhaps most elegant. In standard quantum mechanics, an entangled pair shares a single wave function. It describes the probabilities for the whole system, but it's an abstract mathematical thing, spread out potentially over vast distances.
Right, the spooky connection is encoded in this abstract wave.
Yes. What this model seems to be suggesting, especially with the ER-EPR interpretation, is that this abstract wave function has a physical geometric reality. It is the string, the wormhole connecting the endpoints.
The wave is the connection.
The stringified wave is the physical wormhole geometry that embodies the entanglement described by the wave function. The wave's weird non-local properties, the spookiness, are literally encoded in the geometry of this physical connection through space-time.
So it gives a physical picture for entanglement's weirdness.
Exactly, a tangible geometric interpretation for that spooky action.
Okay, let's try to pull all these threads together. If we synthesize this model using the ER-EPR lens, what kind of universe are we looking at? What's the big picture?
Well, in this synthesized view, the most fundamental layer of reality isn't space-time. It's not particles, not even the strings of traditional string theory. It's quantum information.
Entanglement.
Information is fundamental. That's the idea. The universe, at its deepest level, might start with abstract quantum entities, call them qubits, preparticles, whatever, that become entangled with each other. And the network of these entanglement connections defines space itself. An entangled pair is like a basic unit. Two nodes, the particles, connected by a link, the entanglement wormhole.
So the universe is fundamentally a quantum network.
A vast dynamic quantum network. And the geometric reality we experience as spacetime.
Is an emergent property of this network's connectivity.
Precisely. Connecting it back, each entanglement link manifests geometrically as one of these Planck-scale Einstein-Rosen bridges, or wormholes. The gravitational strings in the model are these emergent wormholes. Space-time is the large-scale tapestry woven from this immense network of tiny connections.
And gravity, where does that fit in?
Gravity itself isn't fundamental in this picture. It's not a force mediated by gravitons in the usual sense, nor a specific string vibration. It's more like thermodynamics. It's the large-scale, average, classical description of the underlying statistics and dynamics of this entanglement network.
Like temperature emerging from the motion of molecules.
Exactly like that. It's a collective emergent phenomenon.
And particles and forces, the stuff of the standard model.
They would also be emergent. The particles are the nodes in this network, their properties arising from whatever fundamental quantum rules govern the nodes. The forces are interactions propagating across the links, across the wormholes. The whole particle zoo and the forces we see are emergent structures arising from potentially much simpler rules governing quantum information and entanglement. It's a radical perspective shift.
Okay, just to really crystallize this synthesized view for everyone listening, we're saying the fundamental thing isn't particles or strings, but entangled nodes.
Right.
Space-time isn't a background. It emerges from the network of these nodes. No need for compactified dimensions in the same way, maybe?
Potentially, although we'll get back to dimensions. But yes, emergence is key.
Gravity is a macroscopic property, like pressure or temperature, derived from the network's behavior.
Not fundamental.
Entanglement is the literal glue, the connection that builds space-time.
Yes, the fabric itself.
And wave-particle duality gets a geometric explanation. The wave is the physical string wormhole connecting the point-like ends.
It gives physicality to the wave function, yeah.
Okay, any theory aiming this high has to tackle the big puzzles. What about extra dimensions? Does this emergent model need them, like string theory does?
That's a really good question. Given that the ER-EPR conjecture itself comes out of and is deeply intertwined with the math of string theory and M theory, which do operate in higher dimensions, it seems highly likely that any fully fleshed out, mathematically consistent version of this emergent model would also require extra spatial dimensions. The strings, these wormholes, they would likely be fundamentally higher dimensional objects. Their full structure would exist in some larger 10 or 11-dimensional bulk spacetime, and we only experience a slice.
Okay, so extra dimensions might still be part of the picture. What about the hierarchy problem? Why is gravity so ridiculously weak compared to other forces, like orders of magnitude weaker?
Right, the infamous weakness of gravity. It's about 10,036 times weaker than electromagnetism. Why? Standard string theory has this brane world scenario as a possible answer. The idea is that our universe is a three-dimensional brane embedded in a higher dimensional space. Most forces and particles, open strings, are stuck on our brane, but gravity, closed strings, can leak out into the extra dimensions, the bulk.
Diluting its strength for us on the brain.
Exactly. This synthesized model, built on ER, EPR, and likely needing extra dimensions, offers a very similar, quite elegant explanation. If the strings are actually higher dimensional wormholes, connecting points on our brain, but extending into the bulk,
then the gravity we feel is just a part of the connection.
Yeah, it's like we only feel the ends of the wormhole on our brain. The full strength of the connection exists in the higher dimensions, but only a tiny fraction manifests as gravity in our familiar 3+1 dimensions. It naturally explains the weakness.
It sounds conceptually very neat, but how do we test any of this? Does it fall into the same trap as string theory's landscape problem?
The landscape. Yeah, the problem that string theory seems to predict a colossal number of possible universes, like 10,500 or more, based on different ways to compactify those extra dimensions. With so many possibilities, it's hard to make unique, falsifiable predictions for our universe.
Does this emergent network idea escape that?
Probably not, unfortunately. It seems likely it would just replace the landscape of possible compactification geometries with a landscape of possible fundamental rules for the quantum network, or possible stable entanglement patterns. Without some principle to select our specific universe's rules from this vast landscape, it faces the same challenge. Why this universe, with these laws and constants?
So it might be just as hard to test or falsify.
The lack of unique, testable predictions is a major hurdle for string theory, and this emergent spacetime framework, being deeply connected, likely inherits that issue.
So no clear experiments on the horizon then.
Not direct tests, no. It's currently more of a conceptual framework than a fully predictive theory. But there are potential avenues, conceptually at least. For instance, the model strongly suggests spacetime is fundamentally discrete, built from this network. If future experiments could somehow probe the Planck scale a huge if, and found spacetime to be perfectly smooth and continuous down to the smallest scales, that would contradict the core idea.
Okay, so finding smoothness would challenge it.
Right. And maybe more directly, though technologically completely out of reach right now, if we could somehow manipulate entanglement on a large scale. Imagine creating or destroying complex entanglement patterns in a lab and observing a corresponding measurable change in the gravitational field or local geometry.
Mm.
That would be a direct logical test of the EPR equals emergent spacetime idea.
Creating space-time ripples by manipulating entanglement.
Wow. But yeah, sounds like science fiction for now.
Very much so. So its value currently isn't in making predictions we can test next year. It exists as a powerful pre-theory.
A way to think about the problems. Exactly, a conceptual toolkit for tackling these incredibly deep questions about quantum gravity, entanglement, and the nature of reality itself. Its power is in guiding our thinking. Hashtag tag tag outro.
So wrapping this up, what does this all mean for you, our curious listener? We've journeyed through a pretty radical reimagining of reality today, moving beyond even particles and strings to a universe possibly built from quantum information, where entanglement is the fundamental stuff.
Yeah, and what's really fascinating, I think, is how this framework, as presented in the analysis, seems to independently arrive at and really intuitively phrase the core concepts behind ER-EPR. It manages to blend ideas from string theory, quantum information science, and general relativity into one mostly cohesive story. And it offers these potentially elegant ways of thinking about long-standing mysteries like wave-particle duality or why gravity is so weak.
It definitely highlights this paradigm-shifting possibility that the solid geometric reality we navigate every day might actually be woven from these weird, probabilistic, spooky quantum connections.
Which really leads you to wonder, doesn't it? If space-time itself is just an emergent network of entanglement, does our everyday notion of distance, of separation, fundamentally dissolve at the deepest level? Are we much more interconnected than classical physics would ever suggest?
That's a fascinating thought, and it leaves you, the listener, with this to consider. If reality truly is a network of connections, what other seemingly fundamental features of our universe might turn out to be emergent phenomena? What else might we discover that completely reframes our entire understanding of everything? It's definitely something provocative to mull over.